How's it going, guys? Today in this video, we're going to be going over kind of off to what we did in the last video, where we kind of grabbed the transform function. In this video, we're going to go from a transform function back into our equation, or back to our transform equation. So when we're doing that, we're really only going to be asking for either one parameter, either the a or the b. We're not usually going to solve for both, and you'll know what the equation says. So for instance, on number one, we're saying g of x equals a times x minus h all cubed plus k. I don't see it being that equation, so I'm asking you to solve for the a. But right here on number two, which should be erased, there we go. Look at number two here. I'm asking you to solve for the b value. I've given you an equation with b in it, so I'm asking you to really solve just for b. All right, so you're going to know about what the equation says, which variable to solve for. So let's go back to number one. And there's going to be kind of two ways to solve both of these. And it's just because solving for a is always going to be much easier, just because the a is not inside the parentheses, is not being cubed. So solving for a is always going to be much easier than solving for b. All right. So when it comes to solving for a, what we're going to do is we're going to figure out what our hk point is going to be first. So remember our hk, if you look at our graph, that's going to be the points where the function kind of curves inwards, then back out. Remember, that's the distinct feature of a cubic function, that it curves in, then it curves out. So we call that concavity change because it caves in, it caves out. That's very distinct to cubic functions, to cubic roots. So you do need to know that, and that's where our hk point is going to be. It's a part of the graph of a cubic function where it curves inwards, then back out. So our h is 2, our k is 1, and what we're going to do now is choose another pair of points. It doesn't matter which one you use because it's on the graph, so you can solve for your a either way. So you can use 3, 4, or 1, -2, it doesn't matter. So I'll go with 3, 4. And so all I'm going to do now is just plug these values into the equation. I get 4 equals some a value that I'm solving for, times my x of 3 minus my h of 2, all cubed, plus my k of 1. So from here, I'm just going to go ahead and solve for my a. So I can minus 1 on both sides, so you get that 3 equals a, times 3 minus 2 is 1, and 1 cubed is just 1. So really just a equals 3. So it's as easy as that. You have your a value now, and we're just going to plug it in. So g of x equals my a value 3 times x minus my h value 2, all cubed, plus my k of 1. So figure out your hk point. That's the point where the graph curves into it and curves back out of it. Then plug in your either point or any point you find on the graph to solve for your a. Solving for a's is easy. If this is how we're going to solve for a's, just plug everything in, solve for a. It'll be the easiest way to solve for a. Now, when it comes to solving for b, it's not too bad, but it's going to be a little more work than solving for a. It takes a little more thinking. So on number two, we have g of x equals parentheses 1 over b times x minus h, close parentheses, cubed plus k. So just like we're solving for a's, the first thing I'm going to do is I'm going to figure out what my hk is. It's the same thing. It's the points where the graph curves into the function, or into the point that curves right back out. And that's that -4, 1. So I know my hk is -4 and 1. And now I need to pick either one of my two values right here, x or g of x. Again, it doesn't really make too much of a difference at all. Choose whichever one you want. I'll go with -3.5, 2. Like I said, if you want to go with -4.50, that's okay too. It really doesn't matter. And what we're going to do now is we're not actually going to plug this back into our equation, because if we did, we'll just end up having to cube roots of each side, and it's going to be really confusing. And actually, I'm going to go ahead and show it to you guys why we don't want to do it this way. I wouldn't write this down. I just want to show you guys why we wouldn't really want to plug this in, because it gets really confusing. So if we plug this in, I'll get 2 equals parentheses 1 over b multiplied by my x of -3.5 minus h, so minus -4, which is plus 4, all cubed plus my k of 1. I can minus 1 over, and I get 1 equals parentheses 1 over b times negative 3.5 plus 4, that's 1/2. All of that cubed. So I end up getting 1 equals parentheses 1 over 2b, all cubed. And from here, it's going to be kind of ugly. We got lucky that we have a 1 here, but if you don't have a 1 there, you got to end up taking like the cube root of both sides. It's going to get pretty ugly, right? We're going to take the cube root of both sides. We don't want to deal with that because we don't always know what our numbers are going to be on the left side, because you got like a 4. You try to take the cube root of 4, it's going to be really ugly. So this is why we don't want to just plug in our b value. So I hope you did not write this because it works, but it's going to be, it could be really ugly. It could be really confusing sometimes. So I would not solve it this way. The way I would solve it though is I'll use the transformation rule. So remember that these 2 points right here on the side, this negative 4.50 and this negative 3.52, those are, sorry, I'm trying to remember this right, but our reference points transformed into those points, right? So for instance, negative 1, negative 1, when I plug that into my transformation rule of bx plus h, comma, ay plus k, that gave me my new transform point of negative 4.50. So I plug in the reference point negative 1, negative 1, I get my transform point negative 4.50. When I put in the transformation point 0, 0, I get the hk negative 4, 1. I'm not going to write that down. You should know that. The point 0, 0, my reference point 0, 0 gives me my hk of negative 4, 1. And my other reference point of 1, 1, when I put that into bx plus h as well, and ay plus k, and it gives me my other reference point of negative 3.5, comma 2. So this is what I'm going to use, because when I use negative 1 and I put that into bx plus h, I get negative 4.5. When I put this negative 1 into ay plus k, I get 0. And same thing with 1, 1. If I take this 1, I plug it into bx plus h, I get 3.5. When I take the other one, the y value of the reference point, plug it into ay plus k to transform it into my transform point of 2. So this is the property I'm going to use to actually solve for my b value. And since I only want my b value, I'm only going to care about what's underlined in red. And I'm using the point negative 3.52. So I'm using this second line right here. So all I'm going to do is I'm going to take what's underlined in red and plug it all in. So I'm saying when I have this 1 right here, and I plug that into bx plus h, I should get 3.5. That's what, or sorry, it should be negative 3.5. That's what I should get. So that means I take this 1, my x equals 1, I'm going to take it, plug it in, so I have some b value that I don't know. I should keep that in red or in black. So I have b times the x value of 1 plus my h value of negative 4, so minus 4, should equal that negative 3.5. Right, I'm just kind of going backwards of what we did in the previous video when we actually graphed transform functions. So I have my transform point, and I'm using the transformation rule to get my b value. So what I'm going to do here is just solve for b now. I can add 4 to both sides to get that b times 1 is just b equals positive 1/2. That's how you do it. All right, so you use the transformation points to actually solve for your b value. So I just plug everything in now. So I have g of x. That equals parentheses 1 over b. My b is 1/2, so 1 over 1/2 is just 2 times x minus h. So x minus negative 4 is x plus 4, all cubed, plus my k value of 1. Right? Yeah, k is 1. And that's my equation. So we kind of work backwards to go from our transform points to get our actual b value. And that's what you should get. So from here, I do want you guys to try number 3 and number 4 on your own. And I'll post the answers to that on the board, on your screen actually. So you can see what, how I did it, what I did to solve it out. So remember, A, just plug everything in, solve for A, it's the easiest way possible. For B, you're the easiest way is going to be solving by using your transformation rule. So go ahead and pause the video, try those out, and I'll post the answer to that on the board in a second. Okay? So this is what you should have got for number 3. Number 3, we're solving for an a value, so that's much easier. All I have to do is just plug everything in. So let's actually rewrite this line right here. So I have my x value. Well, I guess we'll just redo the whole thing. That's fine. So anyway, I have my g of x equals a times x minus h cubed plus k. My hk point is -2, -2. That's just the point where the graph kind of curves into it and curves back out. I decided to go with -1, 1. It doesn't matter which point you want to use, that one or -3, -5. You should get the same a value regardless. And when I plug that in, I get 1 equals some a value of my x of -1 minus my h of -2, all cubed minus 2. Add the 2 over, I get 3 equals a. -1 minus -2 is the same thing as -1 plus 2 all cubed. So 3 equals a times -1 plus 2 just 1. 1 cubed is 1. So a equals 3. And you just plug that into the equation with your h and k, and you're done with the problem. G of x equals 3 times x plus 2 cubed minus 2. All right, so that's how you get the a, what you do to get your a. And now for your b, if you haven't done that one, actually pause the video, make sure you pause it, make sure you try it out on your own. It can be a little confusing just seeing me work it, so try doing it on your own to kind of get a better understanding of it. So hopefully you paused and hopefully you did it. And this is what you should have got for number 4. So hk is 1, -1. I decided to go with 5, 0 from the other point. And since I'm solving for my b value, I'm going to use only the x's and only the bx plus h of the function. So I'm taking this 1 right here, my reference point 1, 1, gives me my point 5, 0. So I take that 1, I plug it into bx plus h, and it gives me 5. So I plug in 1, let's make this red right here. So 1 b times x, so b times 1 plus my h value of 1 should give me 5. So b does equal 4. So again, g of x equals 1/4 times x minus 1 all cubed minus 1. So remember, we take this x value, we plug that into bx plus h, and that gives me that 5. So that's how you solve it out. Take the x value, put it into bx plus h, and that should equal 5. And that's how we get this equation right here of this bx plus h plus 1, where x equals 1, and h equals 1 equals 5. You get your b value. And remember, g of x will equal 1 over b, so 1 over 4, x minus h cubed minus 1, and that's the equation you should get. All right? So let's keep on going. Now we're going to talk about graphing cubic functions. We're going to be modeling with a transformation f of x cubed. So this can get a little confusing if you're not fully paying attention, because there's a lot going on. So I'm going to try to break this down as much as I can. So we're told here that mass and volume are related through density, and which is defined as an object's mass per unit of volume. So what that means is that if I have an object with a mass of m and a volume of v and a density of d, the density will be d equals m over v. But since the density is really just a constant, we can rewrite this as mass equals density times the volume. All right, so mass equals density times your volume. So what we're going to do is we're going to use that formula to kind of solve our problems over here. So here on example 3, we're told to use a cubic function to model the situation and graph the function using calculated values of the function, then use the graph to obtain the indicated estimate. So we're told a child's alphabet block, which is a cube, has a density of 0.72 grams per centimeter cubed. So we're told no matter what the actual mass is, no matter what the volume is, my density is always 0.72 grams per centimeter. So what I'm going to do is I'm going to define my variables first. And before I go to define my variables, we need to think about what our volume is going to do. We want the volume of a cube. The volume of a cube is just going to be v equals the length all cubed, right? It's the height times width times length, but for a cube, all that's the same. So just length cubed. So the only variable I need to define is my L, and that's going to equal length. Sorry for the weird L. I just don't want to get the L confused with a 1 in the actual equation. All right. So my volume, the formula for a volume, that's L cubed. So volume equals L cubed, right? Or length times length times length. That's what the volume of the cube is going to be. And my density, that's my constant of 0.72 grams per centimeter cubed. That does not change. It's 0.72. All right. So what I'm going to do with this volume and this density is I'm going to figure out what my equation for the mass of the cube is going to be. Because if I look at my graph and I look at my table, I'm asking you guys to give me the mass of the cube, depending on what the actual length is. I know that what the density is going to be no matter what, so that's my constant. But my length changes. That's what my variable is. That's changing. And so the mass is going to change too. So that's where this equation right here on the top right of your screen, M equals D times V, that's where that comes into play. Because I'm solving for my mass. And I'm saying mass equals density times my volume. So I know my density equals 0.72. And I know my volume is length cubed. So it's length cubed. So mass equals 0.72 times L cubed. And all I'm going to do now is I'm going to plug in all these L values into that equation, and I get my mass. So if you want to pause the video, try doing this yourself. You're just plugging these equations into the formula to get your new mass. But I'm going to go ahead and list them out. It should be 0, 0.72, 5.76, 19.44, and 46.08. So 46, to be clear. 46.08. There we go. So that's what my table is going to be. That's what you get when you plug in those lengths into your formula. Those are the mass that we get when you have a density of 0.72. And they actually graph this function for us on the right. And now what we're going to do is we're going to estimate the length of an edge of a child's alphabet block. It's just a way to say what's the length of the object. That has a mass of 23 and a density of 0.72. That last line of the density of 0.72 is just to let you know that we're using the chart and the graph we just solved for. So it's really just asking us what's the length when your mass is 23. So all we're going to do is just go to our graph right here and just figure out when m equals 23 and see where it intersects with our graph. So the graph equals 23 when our length is about 3.1, 3.2. It's an estimation at the end of the day, so it's about 3.1 or 3.2. So we're going to go to our graph, we're going to draw a line at 23, and that's what we're going to get. Because it's really just saying 23 equals 0.72 L cubed. That's what it's asking us for, and instead of solving it out, I know my y value equals, I know my y is 23, so let's figure out at what x value does y equal 23. And that's what we did. We drew that line and saw where they intersected. So x equals 3.1, or the length equals 3.1 when y equals 23. All right? So I know it's a lot going on, but now that you saw this, you can either re-watch this again to help you understand it now a little better because you know what's going to happen. That could help. Or you can watch me do the next problem. We're going to do that together as well. So on number 2 here, we're told a steel ball bearing weighs with a density of 7.82 grams per centimeter cubed. We're going to figure out its mass depending on what the radius is going to be. So remember, the volume of a sphere, right? A steel ball is a sphere, is 4/3 pi r cubed. Some ugly r. That's pi r cubed. So the only variable I'm really going to have to define is my r. R is going to be my radius. All right. So my volume, I just said, is 4 over 3 pi r cubed. And my density is a constant of 7.82. I cannot write numbers right now, but it should be 7.82. There we go. All right. So I have my volume, I have my density, and remember, mass is going to equal density times volume. I'll ultimately solve it for my mass, so on my equation in terms of m, or in terms, or equal to m. So I want m equals whatever it is, because I'm solving for my m. So I know m equals density times volume, and I have my density and I have my volume. My density is constant, it's always 7.82, which I know m equals 7.82, and my volume, we said it's 4 over 3 pi r cubed, so 4 over 3 pi r cubed. And this is a lot to kind of go through. There's a lot to plug in, a lot to really solve for. I don't want to deal with that. So what I'm going to do is I'm going to take the 7.82, this 4 over 3 pi, and I'm going to combine those all together. I'm multiplying them together, and those are all kind of constants. So I'm going to estimate my pi to be about 3.14, and I'm just going to multiply them all together just to make my life a little easier. So 7.182 times 4 over 3 times pi will give me about 32.76 r cubed. So I'm just going to multiply all those constants together just to get one simple formula that m equals 32.76 r cubed. And now I'm just going to plug all these r's right here in my table into my formula and see what I get. So again, if you want to try this out yourself, I encourage you to do it just to get used to plugging using cubic functions. So you want to pause the video, plug these in yourself, and see what you get, and compare it with what I got. That's great. If not, I'm going to put what we should get. When our radius is 0, we should get 0. When it's 1/2, we should get 4.1. When it's 1, it's about 32.76. When it's 1.5, it should be 110.57. And when it's 2, it should be 262.08. So those are the mass compared to my radius. So what I'm going to do is I'm going to just plug these in and graph my function. So my radius is 0, 0. My radius is 0.5, I get 4.1, which we pretty much add 0 anyways, really close to 0 compared to the rest of the graph. When my radius is 1 at 32.76, so about right here. When at 1.5, it's about 110.57, so about 110. So about right here, I guess. And when it's 2 at 262.08, so way up here. So this is what my function more or less looks like, something close to that. And what I'm asked now is to estimate the radius of a steel ball bearing with a mass of 75 grams and a density of 7.82. So it's really just asking what's my mass, or sorry, what's my radius going to be? And I have a mass of 75, and I have that 7.82, 4 over 3 pi r cubed. Right? It's the same exact formula we just used. I just want to know what's my r going to be when my mass is 75. Sorry, I wrote this wrong. So I go to 75, sit about right here, or right here, draw a line, and it's about right there. There's that line. So they intersect at about, I don't know, 1.3, 1.4, 1.2, something like that. Well, not 1.2 actually, because it's after that halfway line of between 1 and 1.5. But let's just say it's about 1.3. It's approximately a pretty good estimate, about 1.3. So that's where we're going to go. All right. And that's how you do these problems. Hopefully that made more sense. If you need to rewatch it again, please do. It will help a lot just seeing it again. We already kind of understand. You see what's going to happen. So it does help to rewatch it when you kind of already understand. But anyway, guys, that's it for the video. And hopefully this was helpful.